Hello and welcome to this low-level JavaScript mini-series all about the bits and bytes of binary. So far we've seen how binary numbers can represent positive numbers starting from 0. But how about negative numbers? We only have the symbols 0 and 1, or the high and low voltages, so we can't just put a minus sign in front. Instead, what we need is an encoding scheme, and by far the most common encoding scheme is 2's complement. In 2's complement, the leftmost bit takes on a special meaning, indicating the number is negative if this bit is a 1. If you're particularly quick, or you've thought about this before, you might think that this could lead to having 2 zeros. One where all the bits are 0, and another where the leftmost bit is a 1, and the rest are all zeros. Fortunately, 2's complement takes care of this, and the only 0 in the encoding is when all bits are 0. To understand how this encoding really works, let's take a look at a number line for a 4-bit signed number. In the middle we've got 0, which, as already mentioned, is represented by the bits 0, 0, 0, 0. Then, moving to the right, we have the positive numbers 1, 2, 3, 4, 5, 6, and 7, represented by the bits in the expected way. However, if we move to the other side of the number line, -1 is actually represented by 1, 1, 1, 1. -2 is actually represented by 1, 1, 1, 0, and so on, counting downwards in binary until we reach -8. If we take our number line and we wrap it around into a circle, and we follow the binary numbers around clockwise, you'll notice that they do actually count up continuously. Hiding behind this strange encoding is actually an interesting mathematical object, with interesting properties when it comes to operations like addition and subtraction. For example, if you want to calculate 1 plus 2, you start at 1 and you move 2 units around the circle, arriving at 3. But what if I want to calculate 1 minus 3? Well, 1 minus 3 is actually just 1 plus minus 3. So starting at 1, we can add 13, which is the binary number that represents -3 on this circle. If we walk 13 steps clockwise around the circle, we'll end up at -2, which is the correct answer. This is a very useful property indeed. In the last episode, we saw how CPUs do addition with logic gates, and that exact same circuitry can be used to add negative numbers together, at the subtle cost of anyone using this system having to know about the details of this particular encoding. If you're observant, you'll have noticed that for a 5-bit number, -1 would actually be represented by a different set of bits than in a 4-bit number. Namely, they'd be represented by the bits 1, 1, 1, 1, 1. And it's not just -1. For any given number of bits, every representation of the negative half of the number line will be different. So how can we easily turn a negative number into a 2's complement binary number for a pre-decided number of bits? The answer is with a fairly simple process. First, we need to get the binary representation for the absolute value. Then we need to add at least 1 0 in front, because we need a sign bit, so we can 0 extend. Now, to get the negative form of this number, we'll invert the bits using not, and then we'll add 1. The resulting bit pattern represents our negative number. If we take another look at our abstract number circle, you can see why this works. When the bits are flipped, we always arrive at one number before the one that we want, and we just have to add 1 and take another step around the circle to get to the right answer. Now, we can create a FromSigned method, which will let us provide a negative number as well as a positive number to be converted into our binary representation. It's going to be static, and it will take a number n. And just like in FromUnsigned, we're going to check if n is an integer, and already return our special case for 0, which still applies here. Then we can get the binary representation of the positive form of this number using binary.FromUnsigned and math.absolute to ensure that our input is indeed positive. The number of bits that we'll have in our final output is one more than the number of bits in unsigned, because the extra bit is needed to represent the sign. So we can create a copy of that positive number and 0 extend to the required number of output bits. At this point, if n was actually already a positive number, we could just return with 0 sign bit, since it's now a properly encoded signed version of this number. If it's not though, we can flip all of the bits using not and add 1 to that. We can get 1 using FromUnsigned and 0 extending it to the right number of bits. And finally, of course, because add gives us a binary number that has an extra bit, which represents our carry bit, we'll need to return a new binary whose bits are the bit array, but skipping that first bit using the slice method. Now let's try this out. If we log out binary.FromUnsigned -5, then the output is the 4-bit binary number 1011. Which we know from earlier is indeed -5. But it would be nice to be able to convert our 2's complement binary representation back into a real JavaScript number as well. So let's just add one more method that will perform the inverse operation. If the first bit of the number is 0, then the number is positive, and we can just return this.toNumber. Otherwise, it must be negative, and we can do the inverse operation. Now, we had to add 1 before, so now we're going to need to subtract 1. But we only have an add method, so subtraction is just going to be the addition of a negative number, so we can simply add -1. But this poses a problem, because if we try to get -1 using binary.FromSigned, this number won't have enough bits. And we can't use 0 extend, because that will just make the most significant bits 0, meaning that our number won't be negative anymore. Luckily for us, -1 in 2's complement is always the number where every bit is just a 1. So we can get the bits in an array for -1 using this.bits.length and create -1 manually by instantiating a new binary with these bits. Now we can get the positive version of the number by adding -1 and inverting the bits with not, and again, because this gives us a carry bit, we're going to need to strip that carry bit off and return negative positive number.toNumber. Let's make sure this works by adding a call to toSignedNumber, and -5 does come out on the other side. So to recap, we learned that computers can work with negative numbers as long as they use a special encoding called 2's complement. 2's complement encoding represents an abstract mathematical idea where the number line is actually turned into a circle, and because of this, addition continues to work as normal. We can use simple operations to transform our number from a negative representation back into a positive.